If you rewind history to the late 1950s, the space race doesn't look like a foregone conclusion. At the very beginning, the United States was not the frontrunner. In fact, when the world watched Sputnik cross the sky in 1957, it seemed as if the Soviet Union was years ahead, faster, bolder, and more willing to take risks. Newspapers across America described the event as a technological earthquake, and for many citizens, it raised a simple but unsettling question. Could the United States catch up? What followed became one of the most transformative scientific competitions in human history. But the deeper you look into the story, especially in light of declassified documents, financial reports, and engineering records, the more complex the answer becomes. The United States didn't win the race because of a single breakthrough or a single decision. It won because of an entire ecosystem. Universities, private companies, engineers from dozens of fields, and a national commitment that reshaped everything from school classrooms to industrial production. This wasn't just a race to build rockets. It was a race to rethink what a country could achieve if every part of society pulled in the same direction. In the early years, though, there was nothing inevitable about America's victory. The Soviet program produced a series of rapid successes. The first satellite, the first dog in orbit, the first human in space, the first woman in space, the first spacewalk. To many observers of the time, it looked like a clean sweep. And yet, quietly, behind the scenes, the U.S. was building something far more sustainable, a program not just focused on symbolic milestones, but on long-term capability. As engineers began laying the foundations of what would become NASA's most famous projects, the American scientific community started expanding at a speed that had no historical precedent. Universities doubled down on physics and engineering. Government labs coordinated with private contractors in ways that had never been attempted before. And in offices across the country, planners were already thinking decades ahead, not just about reaching space, but about staying there. One of the most significant shifts came from a simple realization. Speed alone would not win the space race. Reliability, precision, consistency, and industrial scale mattered more. Rockets that worked once were impressive, but rockets that could be built, tested, refined, and improved, those would win the long game. It was this philosophy that gradually transformed America's space program. While early Soviet achievements stunned the world, the U.S. was quietly improving materials, inventing new navigation methods, refining guidance computers, and building a production chain capable of producing components with microscopic precision. In the background, an entirely new generation of engineers was emerging, one fluent in the languages of physics, mathematics, and digital logic. And with each passing year, momentum shifted. American missions grew in ambition. Testing became rigorous. Failures, instead of being hidden or downplayed, became lessons. And the national vision, reaching the moon, became the ultimate organizing principle, aligning thousands of minds behind a single objective. But to understand why the U.S. ultimately pulled ahead, we must look deeper at the decisions, structures, cultural factors, and innovations that gave America an advantage not immediately visible on the scoreboard of early space milestones. In the next part, we explore how the United States built the most powerful scientific infrastructure in the world, and why this became the turning point that reshaped the entire space race. Long before the United States placed a foot on the moon, something far more important was happening on the ground. Laboratories expanded, universities redesigned their engineering departments. Private companies that once focused on aviation or electronics suddenly shifted their entire production lines toward spaceflight. It was as if the country had decided that the space race was no longer just a competition. It was an investment in the future. This shift didn't happen overnight. It began with a quiet but powerful understanding. Space exploration wasn't going to be won by a single rocket. It would be won by a system. One of the most critical elements of that system was education. In response to Sputnik, the U.S. launched a nationwide push to expand scientific training. Physics programs doubled in size. New scholarships appeared. Research grants became more common. High schools strengthened their math and science curricula. For the first time in history, an entire generation was being prepared not just to observe technological progress, but to create it. The effect was immediate. Throughout the early 1960s, universities became engines of innovation. They developed guidance algorithms, studied exotic materials, tested propulsion concepts, and experimented with new computing architectures. Many of these breakthroughs didn't bear the NASA logo, but they became essential components of NASA's success. Parallel to this academic revolution came a second foundation: industrial capability. The Apollo program required tens of thousands of parts with tolerances so precise that even tiny imperfections could doom a mission. American manufacturers responded by reinventing their production methods. Companies like Boeing, North American Aviation, Grumman, and numerous subcontractors transformed themselves into precision-driven, high-tech organizations. They learned to mass-produce components whose quality had to be flawless, not just once, but consistently. Internal reports from that era show how extraordinary this process was. Machinists were retrained to work with new alloys. Engineers redesigned tools that had been used for decades. Entire factories changed their structure to meet NASA's standards. Quality control procedures grew so advanced that many modern industries still use principles developed during Apollo. Another turning point was the creation of NASA's research centers, each dedicated to specific domains: propulsion, guidance, aerodynamics, life support systems, materials science. Instead of dispersing expertise, America centralized its best minds. These centers were not just buildings. They were ecosystems where thousands of specialists could solve problems together, share findings instantly, and calibrate their work toward a unified mission. Yet what truly distinguished the U.S. program from its Soviet counterpart wasn't simply scale. It was transparency within the structure. While the public often didn't see failures, internal teams analyzed every setback with extraordinary honesty. Data wasn't hidden from engineers. Errors weren't buried. Each failure became a blueprint for improvement. This culture of open technical critique, rare for its time, allowed NASA to adapt faster than any other organization. When tests failed, designs changed. When calculations proved wrong, teams updated them. Progress wasn't linear, but it was relentless. And then came one of the United States' greatest strategic advantages: computing power. Even in the era of room-sized computers, NASA invested heavily in digital guidance systems. The Apollo guidance computer, though revolutionary for its time, was only one part of a much larger computational ecosystem. Labs across the country were refining simulation tools, running stress models, and calculating trajectories that would have been impossible a generation earlier. By the mid-1960s, the United States had created something the world had never seen before: a national scientific machine capable of solving problems on a scale previously unimaginable. Meanwhile, American industry gained something else: experience. With each new mission, manufacturers, contractors, and research centers built knowledge that compounded like interest. America wasn't just assembling rockets. It was assembling decades of expertise, layer by layer, failure by failure, improvement by improvement. This accumulation of scientific infrastructure, human capital, industrial ability, and computational power formed the backbone of American success. The early triumphs of the Soviet program were undeniably impressive, but they were built on concentrated efforts and narrow pipelines. The United States, by contrast, built a network, broad, sustainable, and capable of growth. The next question, and one we address in the following part, is simple. How did NASA turn this vast infrastructure into a program resilient enough to survive major failures and still push forward toward the moon? Standing on the outside, the space race often looks like a string of spectacular successes: first missions, first crews, first lunar orbits. But inside NASA, the story unfolded very differently. Progress was not a perfect climb. It was a jagged line shaped by setbacks, recalculations, redesigns, and lessons learned the hard way. And it was precisely this ability to absorb failure, analyze it, and rebuild stronger that became one of America's most decisive advantages. In the early 1960s, the U.S. space program faced a series of painful challenges. Rockets exploded shortly after launch. Guidance systems drifted off course. Combustion chambers malfunctioned. Heat shields cracked. Some missions didn't even clear the launch tower. These failures could have crushed momentum entirely, especially in a climate where the Soviet Union was already scoring visible victories. But something remarkable happened. NASA normalized failure as part of progress. Inside the agency, engineers approached every setback with forensic precision. Instead of hiding problems or rushing past them, teams documented every anomaly in excruciating detail. When a mission went wrong, specialists from dozens of fields gathered to reconstruct the event piece by piece, sometimes down to the millisecond. Declassified meeting transcripts from the period show engineers arguing passionately over valve angles, wiring layouts, telemetry spikes, and microfractures in metal alloys. Nothing was off limits. Nothing was too small. Every component, no matter how insignificant, could be the key to understanding what went wrong. This culture of transparency created something incredibly powerful, a feedback loop that made every mistake a step forward. If a rocket exploded, its successor incorporated dozens of improvements. If a material failed, it was replaced with something stronger. If a simulation proved inaccurate, entire models were rebuilt. The Soviets, operating in a more secretive environment, faced their own failures, but they did not always have the institutional infrastructure to analyze them openly. The U.S., on the other hand, had universities, contractors, in-house labs, and independent testing facilities, all contributing to the cycle of improvement. Another essential factor emerged during this era: redundancy. American engineers embraced the philosophy that no single component should determine the success of a mission. If one system faltered, another would take over. If a sensor glitched, auxiliary data would compensate. This approach didn't just reduce risk, it increased resilience. The Apollo guidance computer, for example, was deliberately designed to prioritize tasks when overloaded, ignoring low-priority commands to prevent catastrophic failure. That design decision saved Apollo 11 when alarms rang inside the lunar module just minutes before landing. Redundancy was more than engineering. It was strategic thinking. It turned potential disasters into recoverable situations. Equally important was simulation culture. NASA didn't rely on single rehearsals. They practiced launches, landings, spacewalks, and emergency procedures thousands of times, often under conditions far more extreme than they expected in reality. Engineers intentionally created failure scenarios, forcing astronauts and ground crews to respond under pressure. This wasn't just training, it was conditioning. By the time Apollo missions began, NASA had rehearsed so many malfunctions that crews could respond instinctively to almost any unexpected event. Another overlooked strength was NASA's interdisciplinary approach. Instead of keeping aerodynamicists, computer scientists, chemists, and biologists in separate silos, the U.S. built cross-functional teams. This allowed different fields to solve problems together, a rare approach at the time. It meant a software engineer could speak with a propulsion specialist, or a materials scientist could collaborate with a flight surgeon. This mosaic of expertise made the program more adaptable than any single research group could ever be. Finally, America's political environment, often turbulent and debated, produced something essential: sustained funding. The commitment to reaching the moon created a financial foundation that allowed NASA to plan years ahead. Budgets were debated, yes, but they existed on a scale that enabled rapid testing, rapid learning, and rapid redesign. By the mid-1960s, this combination of transparency, redundancy, simulation, interdisciplinary teamwork, and stable investment forged a program capable of absorbing shocks and emerging stronger. Early Soviet victories were brilliant, but they were narrow. America's victories took longer, but they were built on rock. In the next part, we dive into the heart of the American advantage, the digital revolution inside NASA, the computers, codes, and logic systems that turned impossible calculations into precise trajectories. Walk into NASA's mission control during the mid-1960s, and something becomes immediately clear. The space race wasn't just about rockets. It was about numbers, calculations, logic, a level of computational precision that no human mind could sustain alone. And while the world focused on astronauts and launch pads, the real transformation was happening quietly in the background, inside the machines that would guide every trajectory, every burn, every step toward the moon. This shift began with a simple realization: the complexity of spaceflight was too great for slide rules and intuition. The math behind lunar missions was overwhelming. A rocket leaving Earth had to hit a moving target, then synchronize its velocity with a spacecraft orbiting another world. A guidance error of just a few seconds could mean missing the moon by hundreds of miles. Engineers knew that only digital systems could manage such precision. So the United States made a decision that changed history. It embraced computing earlier, deeper, and more aggressively than any other spacefaring nation. NASA partnered with MIT's Instrumentation Laboratory to develop what would become one of the most influential devices of the century: the Apollo Guidance Computer, AGC. By modern standards, it was tiny, a 1 megahertz processor with barely enough memory to store a few photographs. But technologically, it was revolutionary. It used integrated circuits at a time when most computers relied on bulky transistors. It had real-time task management, error recovery systems, and user prompts that astronauts could interact with mid-flight. This wasn't just a machine. It was an early blueprint of the digital age. But the AGC was only one piece of the puzzle. Across the country, NASA facilities operated massive room-sized computers dedicated to simulation and trajectory modeling. These machines ran thousands of mission profiles, each representing a different combination of conditions. What if the launch window shifted? What if the moon's gravitational influence deviated slightly? What if a burn lasted a fraction too long? Every answer fed into the next model, refining accuracy until the margins approached perfection. The U.S. also excelled in telemetry processing. Sensors across spacecraft produced streams of data: temperature readings, oxygen levels, electrical load, fuel status, vibration metrics. Mission Control didn't just observe this information, it interpreted thousands of numbers in real time, searching for anomalies. This required computing power far beyond what the public knew existed. Some of the most important work happened inside NASA's digital simulation labs. These centers created mathematical environments so detailed that engineers could test entire missions without ever leaving Earth. They simulated spacecraft failures, atmospheric distortions, sensor noise, engine misfires, and even timing delays inside communication networks. The more scenarios they tested, the more resilient the program became. On the Soviet side, engineers were brilliant, but they worked with fewer digital tools. Their designs were elegant and often daring, but they relied heavily on analog systems and manual calculations. America's embrace of computers gave NASA an edge that multiplied over time. With every new mission, simulation data improved. With every improved model, trajectories became safer. And with every safer mission, ambitions could grow. Another critical advantage was NASA's software culture. The code running inside the Apollo computer was written with a level of discipline and structure unheard of at the time. Programmers developed early forms of error handling, priority scheduling, and safeguards against data overload. When Apollo 11's computer nearly reached its processing limit during the lunar landing, the AGC didn't crash. It calmly discarded low-priority tasks and focused on what mattered. That design saved the mission. America didn't win the space race simply because it built bigger rockets. It won because it built smarter systems. Digital infrastructure turned complexity into something manageable. It allowed NASA to simulate faster than anyone else, calculate deeper than anyone else, and react to anomalies in ways no analog system could match. By the time the U.S. prepared for the lunar landing, its computational ecosystem had become a silent partner in every critical decision. Ground control wasn't just a room full of people. It was a network of machines calculating millions of variables each second, ensuring that humanity's first steps on another world would happen exactly as planned. In the following part, we explore another powerful advantage that helped the United States surge ahead: America's unmatched manufacturing ecosystem, the factories, materials, and engineering standards that made building a moon rocket even possible. If you want to understand why the United States overtook the Soviet Union in the space race, you have to step away from the launch pads and look somewhere less glamorous: the manufacturing floors scattered across the country. Hidden behind the iconic imagery of astronauts and rockets was an industrial landscape that had quietly transformed itself into the most capable engineering machine in the world. What made this transformation extraordinary was not just scale, but precision. Spaceflight demanded tolerances smaller than anything most factories had ever attempted. A single component machined 1 millimeter off could ruin a rocket stage. A tiny contamination inside a fuel line could trigger an explosion. A misaligned circuit could cause a guidance failure. America responded by reinventing how things were built. In the early 1960s, companies that had spent decades mastering aircraft production suddenly faced a new challenge: building vehicles that had to survive the vacuum of space. To meet NASA's demands, they introduced manufacturing standards unheard of at the time. Workers retrained, tools were rebuilt. Entire workflows were redesigned to meet requirements that pushed the edges of what was technologically possible. Internal documents from the era show extensive checklists, measurement logs, and protocols that required every part to be inspected multiple times before it could be approved. This rigorous system created not just parts, it created trust. When a component left a factory, NASA could rely on it to perform flawlessly. Some factories became legends in their own right. Machining centers in California and Texas learned to cut exotic alloys. Electronics plants developed new methods for wiring delicate circuits. Composite laboratories experimented with materials that had never been used in aerospace before. Out of this environment emerged the Saturn V, the most powerful rocket humanity has ever successfully flown. But the real miracle wasn't the rocket itself. It was the industrial network that built it. Each rocket stage came from a different region of the country. Each subsystem was crafted by specialized teams. Each instrument required coordination between manufacturers separated by thousands of miles. To manage this complexity, the U.S. developed a system of quality assurance that became a global standard. Engineers tracked every component from raw material to finished assembly. If a piece of wiring burned out during a test, they could trace it back to the exact batch of copper used to make it. This systematic tracking reduced the space for error to near zero, something no other nation managed at the same scale. At the same time, America benefited from a competitive contractor environment. NASA didn't rely on a single factory or a single design team. Instead, different companies competed, proposed solutions, refined prototypes, and pushed one another to innovate faster. When one design failed, another was waiting. When a system showed promise, several companies worked to improve it. This competition fueled creativity and drove technological progress at an unprecedented pace. But it wasn't only big aerospace firms that mattered. Thousands of smaller suppliers, family-owned machine shops, regional electronics producers, specialized chemical companies, provided the parts that made the Apollo program possible. Their collective contributions formed the backbone of American space hardware. Another key advantage was the consistency of U.S. industrial output. Factories could scale production rapidly without sacrificing quality. If NASA needed 10 units of a component, it could get 50. If a part needed redesign, manufacturers adapted almost instantly. This agility proved decisive in the 1960s. While the Soviet Union struggled with bottlenecks and shortages in its centralized system, America had a nationwide manufacturing ecosystem capable of iterating, improving, and producing at extraordinary speed. The result? The U.S. didn't just build space vehicles, it built an infrastructure that could sustain spaceflight. This industrial powerhouse became the hidden engine of the space race. Rockets were the visible triumphs, but factories were the real battleground, and in that arena, the United States had a clear advantage. In the next part, we uncover another dimension of America's success: the political and cultural atmosphere that rallied the nation, unified public opinion, and turned space exploration into a shared American mission. Long before the Saturn V ever roared to life, something profound was happening across the United States. It wasn't technological, it wasn't industrial, it wasn't even scientific. It was cultural. The country had decided, collectively, consciously, and unapologetically, that reaching the moon was not just a government project, but a national purpose. This shift didn't come from pressure or fear alone. It came from a vision articulated clearly, publicly, and repeatedly: we choose to go to the moon. Those 7 words reshaped American identity in ways that few historical speeches have ever managed. They turned space exploration into more than a technological competition. It became a measure of American possibility. Across the country, newspapers printed stories that blended awe with optimism. Television networks broadcast footage of rocket tests and astronaut training with a sense of national pride. Schools introduced new science programs, and children began dreaming not just of airplanes, but of spacecraft. The moon wasn't a distant object in the sky anymore. It became a destination, a visible symbol of what Americans believed they could accomplish when they worked together. What made this cultural momentum so powerful was its breadth. Support didn't come only from scientists or politicians. It came from teachers, workers, engineers, families, and entire communities. Factories celebrated when their components passed NASA's rigorous tests. Cities followed the missions as though cheering for a home team. Astronauts became household names, representing both bravery and technical excellence. Even people who weren't directly connected to aerospace felt emotionally invested in the mission's success. This cultural unity created something rare: political stability around a massive, expensive, long-term scientific project. Unlike many large government initiatives, America's space program didn't constantly shift direction with each election cycle. Leaders from both major parties recognized the symbolic and strategic importance of space exploration. Behind the scenes, legislative cooperation ensured that NASA received stable funding, allowing the agency to plan years ahead, something essential for engineering programs of this scale. This continuity became one of America's hidden advantages. The Soviet program struggled with internal political transitions that created interruptions. The United States had the opposite: a sustained, decade-long commitment. But cultural support did more than influence Congress. It motivated the workforce. Engineers who stayed late in laboratories weren't doing it because it was their job. They were doing it because it felt like they were contributing to something historic. Parents encouraged their children to study science, knowing the country needed more minds capable of pushing the boundaries of knowledge. Universities saw record enrollments in engineering fields. Spaceflight became a source of inspiration, a national narrative, and a unifying symbol, a rare moment where technology and identity merged. There was another subtler element at play: America's optimism. The nation had always possessed a cultural instinct to push frontier lines, whether geographic, scientific, or conceptual. For many citizens, the moon became the next logical frontier, the natural extension of a belief that exploration was part of the country's DNA. Meanwhile, the storytelling power of American media amplified this spirit. Documentaries, news segments, public broadcasts, and even classroom films painted space travel as a shared dream. It wasn't marketed as a contest against a rival nation, but as a collective journey toward the unknown. This optimism fueled resilience. When missions failed, the nation mourned, but it did not withdraw. When countdowns were canceled, people returned for the next attempt. When setbacks occurred, they were framed not as signs of defeat, but as steps toward progress. By the mid-1960s, Americans weren't just hoping NASA would reach the moon, they expected it. And that expectation helped sustain political will, industrial effort, and scientific creativity through every obstacle. The space race was, in many ways, a battle of narratives. One society driven by rapid early successes, the other driven by long-term vision. The U.S. didn't win because it feared losing. It won because it believed in what it could achieve. In the next part, we explore another pillar of American success: the role of international collaboration, scientific openness, and the influx of global expertise that strengthened the U.S. program from within. Walk into a NASA research center during the 1960s, and you might be surprised by what you would hear. Yes, English dominated the hallways, but accents filled the room. German, Italian, British, Canadian, Indian, and Eastern European voices echoed alongside those of American-born engineers. The United States didn't just build a space program. It assembled an international engine of knowledge that became one of its greatest strategic advantages. This wasn't by accident. It was the direct result of America's openness to global talent. Throughout the mid-20th century, the U.S. became a magnet for scientists, mathematicians, and engineers from around the world. Some arrived for academic opportunities. Others came for industrial work. Many were drawn by the promise that their research wouldn't be buried, but developed and supported. And in NASA's early years, this mix of perspectives helped the agency solve problems that would have been far harder within a closed, homogeneous system. Inside laboratories and design rooms, ideas blended in ways no single national tradition could achieve. European engineering precision intersected with American manufacturing scale. British mathematical traditions complemented U.S. computing power. Specialists from Asia contributed innovations in materials science and fluid dynamics. Each brought a unique way of thinking. What made this collaboration powerful was not just diversity, it was structure. NASA organized its centers so that talent could flow across disciplines and regions. A propulsion expert from one state could work directly with a software innovator from another country. A materials scientist from a foreign university could join a U.S. team studying thermal protection systems. This created a cross-pollination of ideas that accelerated progress. At the same time, America's universities became global hubs of scientific learning. During the space race, international students filled engineering programs at MIT, Caltech, Stanford, Purdue, Georgia Tech, and dozens of other institutions. Many stayed, others returned home with new knowledge, but all contributed to a worldwide scientific network that strengthened U.S. research indirectly. NASA also cooperated with allied nations on countless scientific studies. British observatories provided astronomical data. Canadian specialists worked on satellite technologies. Australian tracking stations supported communications. European laboratories exchanged findings about materials and fuels. In a race where precision mattered, this global integration gave the United States something priceless: a broader pool of insight. While the Soviet program operated in a more centralized, insulated environment, the U.S. built a model driven by open scientific exchange. Difficult problems didn't stay trapped within one institution. They were attacked from multiple angles by people with different backgrounds. Another underrated factor was the American scientific publishing culture. U.S. researchers shared vast amounts of information publicly through journals, conferences, and academic collaborations. While classified work remained protected, everything else, physics, astronomy, computer science, engineering, was open for the world to study. This openness allowed U.S. institutions to draw from the entire global knowledge base while simultaneously contributing to it. Even today, historians reviewing the era emphasize how unusual this was. The space race is often framed as a contest between two nations. In reality, America's approach made it the center of a worldwide scientific community, one that ultimately helped power NASA's breakthroughs. Countless innovations crucial to the Apollo program had global fingerprints. Thermal shielding research borrowed insights from European labs. Propulsion studies incorporated ideas from international combustion experts. Orbital calculations benefited from mathematicians educated in foreign systems. Early computing theory came from minds active on multiple continents. This wasn't outsourcing, it was cooperation, scientific, academic, and industrial. The United States became the gravitational center of space research because it welcomed talent, nurtured innovation, and created an environment where ideas could move freely. By the late 1960s, NASA's strength was not just American dedication, it was global expertise channeled through American infrastructure. And that combination proved unbeatable. In the next part, we explore yet another dimension of U.S. success that quietly shaped history. How America built a communication and tracking network so advanced that it became a strategic advantage all on its own. Long before astronauts climbed into their spacecraft, long before the Saturn V shook the ground beneath Florida, an entirely different structure had to be built. One you couldn't see from launch pads or control rooms. It wasn't made of metal, fuel, or circuitry. It was made of antennas, radar domes, relay stations, tracking centers, and communication lines stretched across the globe. In the space race, rockets got the glory, but networks won the missions. What the newly examined historical records make clear is this: the United States created the most sophisticated space tracking and communication system on Earth, and that system became a decisive strategic advantage. It began with a challenge no nation had ever faced. To send humans beyond Earth orbit, you needed more than propulsion. You needed to maintain contact over vast distances, monitor spacecraft conditions in real time, track trajectories with exquisite precision, and update guidance commands instantly if something went wrong. And Earth's rotation made this nearly impossible. A spacecraft could disappear over the horizon in minutes, leaving one ground station blind. NASA solved this by building a global ring of communication, a network that wrapped around the planet like an invisible belt. In California, engineers developed deep space antennas capable of picking up faint signals from hundreds of thousands of miles away. In Australia, massive radio dishes were constructed to catch transmissions when American stations dipped out of view. Across Spain, islands in the Pacific, remote Atlantic outposts, and even naval tracking ships, the U.S. deployed a web of receivers and transmitters that allowed mission control to stay in touch with astronauts every second of their journey. This wasn't just infrastructure. It was coordination at a scale no other nation attempted. Each tracking center had to be synchronized down to fractions of a second. Each antenna had to compensate for atmospheric distortion. Each relay had to hand off signals without losing critical data. The system stitched together land-based telemetry, ship-based observation posts, satellite relays, high-gain antennas, and encrypted communication lines. For the first time in history, humans could maintain continuous contact with a spacecraft traveling beyond Earth's immediate influence. This gave the United States something the Soviet program never fully achieved: global oversight of every second of spaceflight. If something went wrong, if a spacecraft drifted, if telemetry changed, if a system flickered, NASA could detect it immediately, no matter where the spacecraft was. That rapid awareness saved missions many times. It also enabled flexibility. If weather shifted, crews could adjust. If timing changed, burns could be recalculated. If anomalies appeared, mission control could react instantly. One internal report described the network as a nervous system with Earth as the body. Every antenna was a sensory organ. Every control center was a processing node. And Houston was the brain, absorbing, interpreting, reacting. This global network did more than guide spacecraft. It united thousands of people across continents in a single coordinated effort. Meteorologists in one hemisphere supported decisions made in another. Engineers in Australia relayed data measured in California. Tracking ships in the Indian Ocean whispered telemetry across sky-spanning arcs of radio waves. By the late 1960s, the Deep Space Network had become a marvel of engineering, unmatched anywhere in the world. Its antennas could detect signals so faint that their power was weaker than the energy of a falling snowflake. The precision of its tracking was so high that it could locate a spacecraft with an error margin smaller than the width of a human hand, from hundreds of thousands of miles away. And its reliability gave America something priceless: confidence. Confidence that missions could be monitored. Confidence that corrections could be transmitted. Confidence that human lives were never lost to silence. While rockets were symbols of ambition, the network was a symbol of control, the quiet guarantee that every plan could be supported until the very last second. This system did not grab headlines. It didn't appear on magazine covers. It wasn't celebrated like astronauts or engineers. But without it, the United States could never have attempted a lunar landing, let alone succeeded. In the next part, we explore a component of victory that is even more subtle: the psychological and organizational stability inside the American program, which turned pressure into discipline and crisis into coordination. From the outside, the space race looked like a battle of technology. Rockets, capsules, computers, astronauts, a spectacle of machines and human daring. But inside NASA, those spectacular scenes rested on something far less visible: the ability to remain calm under enormous pressure, to make precise decisions while the entire world held its breath, and to maintain order inside a system where even a minor error could cost lives. This psychological and organizational stability became one of America's quietest advantages. Every mission carried extraordinary stakes. Journalists broadcast updates across the globe. Schools stopped classes to watch launches. Politicians monitored progress, as though national pride depended on every burn and maneuver. Meanwhile, inside mission control and engineering labs, teams worked with an intensity rarely matched in peacetime. Yet the most striking part of the historical record is not the stress. It's how effectively NASA managed it. Instead of yielding to pressure, NASA institutionalized procedures for controlling stress, maintaining communication clarity, and ensuring that decisions were made systematically, not emotionally. One of the agency's most important tools was structured communication. Flight directors and controllers followed strict phraseology. Reports were delivered in concise formats. No one spoke unless necessary. Every message was recorded, repeated, and confirmed. This wasn't formality. It was survival. Clear communication stripped away panic and kept every person focused. Another key pillar was the culture of role specialization. Every station in mission control had a specific domain: propulsion, life support, guidance, systems, trajectory, and each specialist knew exactly where their authority ended and someone else's began. This prevented confusion in high-stress moments. When an anomaly appeared, the relevant controller led. Everyone else stayed silent until called. This disciplined structure allowed NASA to act with a single voice, even though hundreds of people were involved in each mission. Another essential advantage was simulated stress conditioning. NASA didn't just prepare equipment for failure, they prepared people for failure. Astronauts underwent simulation after simulation, some lasting hours, others entire days. Mission control teams practiced failure cascades, communication dropouts, instrument malfunctions, environmental warnings, guidance errors. Instructors often introduced multiple faults at once, forcing controllers to make rapid decisions without losing focus. These simulations were not meant to scare participants. They were meant to inoculate them against panic. The idea was simple. If you've already experienced a disaster 20 times in practice, you can stay calm when a real anomaly appears. The results were remarkable. When unexpected alarms triggered during the Apollo 11 landing, the crew and controllers responded with textbook precision. They didn't freeze. They didn't argue. They followed procedures crafted through countless rehearsals. Another aspect of NASA's psychological resilience came from leadership philosophy. Flight directors were trained not as commanders, but as coordinators. Their task was to synthesize information, set priorities, and make decisions based on data, not ego, emotion, or speculation. This created a leadership environment where authority was respected but not feared, and where information flowed upward reliably. The agency also built a culture of non-punitive reporting. Engineers were encouraged to speak honestly about problems without fear of retribution. This transparency created an environment where potential issues surfaced early, before they escalated into crises. In contrast to organizational cultures where problems are hidden, NASA's approach gave it a tremendous advantage in risk reduction. One more component rarely discussed is the emotional trust within teams. Astronauts had deep confidence in the engineers who designed their spacecraft. Mission Control trusted the specialists monitoring data. Technicians trusted supervisors. This psychological bond wasn't accidental. It grew out of years of collaboration, shared tests, and collective problem-solving. When people trust one another, they act faster, coordinate better, and stay stable under pressure. By the late 1960s, NASA had become more than a space agency. It was a disciplined psychological machine, a human system engineered for high-stakes performance. While technology allowed Americans to reach the moon, it was human steadiness, the calm voices, the unwavering teamwork, the structured decisions that ensured those technologies were used with precision. Now in the final part, we bring all the threads together and reveal the overarching answer to the question that sparked this journey. Why did the United States ultimately win the space race? And what does that victory actually mean? Looking back at the space race from today's perspective, it's tempting to reduce the story to a single moment. The American flag on the lunar surface, the triumph of Apollo 11, the global broadcast that stopped the world. But the truth revealed by historic records, engineering archives, and decades of retrospective analysis is far more complex and far more meaningful. The United States didn't win the space race because of one rocket or one mission or one brilliant idea. It won because its entire system, scientific, industrial, cultural, and organizational, aligned around a shared goal in a way the world had never seen before. And this alignment unfolded in layers. First came infrastructure, the universities, research labs, manufacturing plants, test facilities, and computing centers that gave the U.S. the ability to innovate at scale. These institutions provided the raw power behind every engineering breakthrough, every simulation, every material design, every prototype. They formed a national research engine with thousands of moving parts, all synchronized toward progress. Then came industry, a competitive, flexible, and massive industrial base capable of building spacecraft with microscopic precision and adapting to new requirements at astonishing speed. Whether it was a valve, a heat shield tile, or a guidance circuit, American manufacturers could produce it, test it, refine it, and deliver it repeatedly and reliably. Layered on top was culture. The United States cultivated a national conviction that reaching the moon was not only possible, but necessary. This created resilience, public support, and political stability. It turned a scientific challenge into a shared mission that millions of people emotionally invested in. Another essential ingredient was global expertise. America welcomed scientists, engineers, mathematicians, and thinkers from every corner of the world. Their knowledge, shaped by different academic traditions and engineering philosophies, blended into a uniquely powerful alloy of ideas. The U.S. didn't just use talent, it amplified it. The country also gained a tremendous edge through communication networks. By building the world's strongest tracking and telemetry infrastructure, the U.S. ensured that no spacecraft was ever out of reach and no anomaly went unnoticed. This global network created a level of control and situational awareness that transformed missions from risky experiments into coordinated operations. And at the heart of it all were people, the steady voices in mission control, the engineers who stayed up through countless nights, the test pilots who risked their lives, the computer programmers who wrote code line by line, the machinists who crafted flawless hardware, and the scientists who imagined solutions when none seemed possible. Their discipline turned pressure into precision. Their persistence turned setbacks into milestones. Their teamwork turned a distant dream into a real footprint on the moon. When all these elements merged, they created something no blueprint could capture. A system capable of improving itself continuously, learning from failure, and growing stronger with every challenge. The Soviet Union achieved extraordinary feats, historic, courageous, and groundbreaking. But their early successes were built on narrow pipelines of effort. The US, by contrast, built a structure that could sustain innovation indefinitely and eventually surpass every rival through scale, stability, and adaptability. By 1969, the victory was not just technological, it was systemic. The moon landing wasn't simply the outcome of a race, it was the expression of a national ecosystem that had spent years expanding, refining, and preparing itself for the most ambitious goal humanity had ever attempted. In that sense, the question, why did the United States win the space race, has a clear answer. Because it built a world where winning became possible. And that world didn't disappear after Apollo. It shaped satellite technology, computing, telecommunications, materials science, and countless industries that define modern life. The space race ended on the lunar surface, but the legacy of America's victory continues orbiting above us every day.